Okay, next we're going to look at an example that throws a curveball at us, and we'll look at also a strategy on how to deal with that curveball once we get there. But for now, let's read the problem carefully. So what do we have? We have a water tank, and it is in the shape of an inverted circular cone. So there's a couple things going on here. A circular cone just means a cone where the base is a circle, because in fact, in general, you can have cones with any polygon for the base. So this just means we have a circle for the base of the cone. And then inverted means it's upside down. So really all that means is you've got something like this. I'm actually going to use the black pen for this. Okay, so we've got the base, which is on the top since it's inverted. And then the cone comes down like that. That's what we're talking about. So just one of those paper cups that you get sometimes at the water fountains. All right, and we're given some information about this. It's got a base radius of 2 meters and a height of 4 meters. So the base radius is just the radius of the base, which is a circle, right? Because circles have radiuses. So really the base radius is just this distance here. So we're told that that is 2 meters. All right, and we're also told that the height of the tank is 4 meters. So I'm just going to write 2 and 4 for that. But it's understood that those are in meters. All right, so that's the first sentence. What else are we told? That water is being pumped into the tank at a given speed. We're at this rate, 2 meters cubed per minute. Right. So, well, here's an example of a drawing that's not so fancy, and it doesn't really need to be fancy. This is just a diagram. It's not a masterpiece that's going to be in a museum somewhere. Right. It's just a diagram to help understand the situation. So I'm just going to write the word pump with a box around it, and I think that makes the point. So let's say it's pumping water into the tank, and I'll just draw an arrow to indicate which way the water is going, just to help us digest the information in this problem. So and we know how fast the water is being pumped in there. It's 2 meters cubed per minute. Okay, what is the last part? Here's the question at the end. Now find the rate at which the water level is rising. So there's water in this tank, right? If the pump is pumping water in, there's water in this tank. And it's going to be anywhere between almost empty or almost full or completely full, right? It can't go beyond that. You're not going to have more water than a full tank, and you're not going to have less water than an empty tank. So the water is going to be somewhere in between. So I'm just going to draw the water like this. That's why I saved the blue, just to make it stand out a bit. So you can see we've got another cone here, right? Because gravity is going to force the water to go to the bottom of the tank, but since it's an inverted circular cone, then the water is going to occupy a cone as well. So, and well, that cone is going to have its own parameters. It's going to have a radius and a height as well, except those ones, that's going to be variable, right? Because as water goes into the tank, this cone is going to grow, both in this radius here, and as well as the water level. So those are going to be probably our variables. And in fact, if you read the rest of the sentence, find the rate at which the water level is rising. So find out how fast this distance here is changing or growing at the particular moment in time when the water is 3 meters deep. So yeah, we definitely are going to need a variable to measure the water level. How about we call it h for the height of that smaller cone formed by the water. And then, well, since we've got a radius for the tank, why don't we also write down a radius for the water? Because that's going to be kind of following the same pattern, but it's not going to be constant. It's going to be changing, right? As the water goes into the tank, this radius is going to be growing just like the height is. All right, so that kind of gives you a hint on what variables to use when you start by labeling your variables. We got a radius, we've got a height. We're also going to want volume, right? Because we've got water being pumped into the tank at a rate of 2 meters cubed per minute. We need to express this as a rate of change of something. Well, this is a rate of change of volume. In particular, it's the rate of change of this blue volume, right? It's the water's volume, not the tank. The tank has a fixed volume. It's always going to be whatever if the tank isn't moving, it's not growing or shrinking, the volume is going to be constant. But as the water gets pumped into the tank, the water's volume is going to grow, and it's going to grow based on how fast the pump is putting water into the tank. So let's write that as a variable as well. So let's say V. And you don't want to just write V equals volume here. That would be a mistake. we want to say V is the volume of the water. Well, actually, that's all you need to say, right? The volume of the water. And what units will we use? Probably meters cubed, since this rate of change is given in meters cubed per minute. Let's go with meters cubed. And then we can just understand that time is measured in minutes for this problem. So later on, if we have to take that into account, we'll just remember that time is the unit of time is the unit in which time is being measured is minutes. All right, so what are our other variables? Radius of the cone formed by the water and the height of the cone formed by the water. So let's go R. We can even say base radius, because just to be more specific. So R is the base radius of the cone formed by the water. And what are we going to measure that in? Well, it looks like the water level is measured in meters at some point. So that's a parameter corresponding to length or distance as well. So why don't we stick with that? Let's use meters to measure the radius, and then that way it'll be compatible with our volume, which is measured in meters cubed. So those units will be compatible. And well, so for H, that's going to be our water level, and that'll also be in meters. Okay, great. So we got our variables. Hopefully we got all the ones we need, and we'll know when we go to write down our relationship, or more in particular when we go to translate the problem into a mathematical one. If we aren't able to do it, then we probably are missing some variables. Okay, so we got to outline what is given and what we're trying to find. Let's start with what's given. What are we told? Well, we're told right here, right? We were told at the beginning that the water is being pumped into the tank at a rate of 2 meters cubed per minute. So that tells you that the rate of change of volume, so dV dt, is equal to 2. Right? If I understand that that's measured in meters cubed per minute. And what do we want? What are we asked to find? Well, we want to know what we were told to find the rate at which the water level is rising. So that's the rate of change of this variable h. Right? So we want dH dt. And we want it at the particular moment in time when the water is 3 meters deep. So in other words, we want dH dt exactly when h itself happens to be equal to 3. That is really what we want to do. Okay, so we need to get a relationship between volume and height. And that's how we can get a relationship between these two rates of change, and we can finish solving the problem. All right, so how are we going to do that? Well, we need a formula, right? What's the formula for volume of a cone? And if you don't remember, that's totally reasonable. It's not one you use very often, so I'm just going to supply it right here. But of course, you could look it up, right? Just Google it or look it up in a book if you have one handy. But in any event, here's the formula for volume. It's 1/3. Here's a nice way to remember it too. If you want the volume of a cone, start by calculating the area of the base, this circle, and multiply it by the height of the cone. And that really, if you started with that, what you'd really get is the volume of the cylinder that is this length and has this base up here. But if you actually want the cone, you just multiply it by 1/3. So pi r squared, that's the area of the base circle, multiply it by the height, and then multiply it by 1/3 afterwards. And that'll give you the volume of a circular cone. And here's the curveball. Here's the thing that's going to make this challenging. This is a relationship between volume, radius, and height. We're only given information about how height is changing and how the volume is changing. If we differentiate both sides with respect to time here, we're going to introduce an equation that has many quantities. It's going to have dV dt, it'll have the rate of change of volume, it'll have the rate of change of the radius, and the rate of change of the height. But we aren't given the rate of change of the radius. We're only given the rate of change of the height. So really that's going to cause a problem. There's several ways to deal with that. One way would be just to ignore the problem for now and just proceed like nothing's wrong and then fix it later. And that can be done, but it ends up being significantly more work, and it gets quite a bit more technical, and there's way more opportunities to make mistakes. So instead of that, it's a lot easier to fix it now. So here's the way to do that. You see this picture of the cones within the cones? There's another way to look at this. If I were to connect the center of this base all the way to the tip of the cone and just draw a vertical line down like this, what you'd have is a triangle within another triangle, right? And actually, if you're willing to accept that if the pump is not shaking the cone all over the place and the tank is staying still and it's not being driven around on the back of a truck or anything, this water level would be flat. And if the cone is vertical, this is going to be a right angle. And this is also going to be a right angle since it's a cone. Okay, well, with that in mind, let's draw another picture here, which is just a side view. And in particular, just a side view of this triangle, right? I just want to just focus on this for now. Okay, so I'm going to draw this one in blue just so you can see how it matches up, right? And what we'd have, well, a right angle here and a right angle here. And what else can we label? Well, this top distance is 2, right? Because this is like the base radius up here. And then this distance here is equal to 4. What else do we have? This distance here, that's the R. So we can label R here. And then what about this distance here? This is going to be H, right? Because that's this side here. All right, so with that in mind, we can actually make the following claim. Similar triangles, right? Both of these triangles are similar. They both have a right angle on the top left corner. On the top right corner, these two angles are the same because those two lines are parallel. So you know that these two angles are identical. And then for the bottom angle, they literally share the same angle. So these two triangles that you see both have all the same angles. So any corresponding pair of sides must have the same ratio. So in particular, the ratio of the radius to the height, so R over H, that has to be equal to the radius of 2 over 4. Another way to think about this, if you're not convinced by that, just imagine if you consider the angle down here and you computed its tan. Well, your opposite over adjacent for the smaller triangle would give you R over H, which is right here. But if you compute tan of this angle using the opposite over adjacent for the larger triangle, you get 2 over 4. But it's the same angle in both cases, so its tan should be the same. So that's why you can get this equation in that manner. But 2 quarters is of course 1/2. So you get that the radius divided by the height is equal to 1 over 2. So really, what this means is we can say that the radius is equal to 1/2 of the height. Right? Because the water is trapped in this larger cone, the radius and height of the cone formed by the water has to follow the same ratio as the radius and the height of the entire tank. That's really what it comes down to. And this triangle is just evidence of that. But the important conclusion here that we're going to use for the problem is this one right here. Okay, the radius is equal to 1/2 of the height, because that's going to allow us to turn this relationship into just a relationship between volume and height. So let's plug in 1/2 height for the radius, and we're going to get 1/3 pi times h over 2 squared times h, right? Just plugging in h over 2 for r. Well, what's that going to look like? Well, you're going to get volume is equal to, well, okay, let's work things out carefully. Start with the number 2. If I square the h over 2, right, because that's what happens, h over 2 is getting squared, that's going to be like h squared over 2 squared. So that'll be like h squared over 4. So there's a 4 on the denominator, but there's also a 3 on the denominator of this fraction. So when you multiply those out, you're going to get a 12 on the denominator. So let's just start with that. And then what's the numerator going to be? Well, we'll have 1 times pi times h, but then you'll also have the numerator of this fraction, which is h squared. So you'll have 1 times pi times h squared times h. That's going to end up giving you pi h cubed. So that's what you get if you carefully combine all these fractions into one fraction. You'll end up getting pi h cubed over 12. And that's the relationship we're going to use here. So we want to take the derivative of both sides of this equation with respect to time, because that's going to be our next step, right? So we want the derivative with respect to time of the volume is equal to the derivative with respect to time of the right-hand side, which is pi h cubed over 12, right? And we can go a little further here. We can simplify this by just the pi over 12, that's a constant multiplier. That can be pulled right out of the derivative. And over here on the left-hand side, that's just going to become dv dt. So we'll have dv dt is equal to pi over 12 times the derivative with respect to time of h cubed. And now, this we can tackle, right? H cubed, that's a power rule, but since h is the inside function and we're differentiating with respect to time, and h is a function of time, we have to use the chain rule. So what we're going to get is dv dt is equal to pi over 12 times 3h squared, that's the derivative of the outside function with the inside function left alone, multiplied by dh dt. Okay, and if we now clean everything up, what you're really going to get is dv dt. Well, we got 3 on the numerator, 3h squared times pi on the numerator. If you reduce this 3 and the 12, that'll just become 1/4, right? And we'll just be left with a pi and an h squared on the numerator. So you're going to have pi h squared over 4 multiplied by dh dt. And that's about as much as you can simplify this. So, well, what else do you do now at this stage? Well, we want to isolate for the quantity that we're looking for, which is dh dt. We want to find the rate at which the height is changing. So we want to solve for dh dt. So get everything else on the other side of the equation. So take the 4, multiply it up to the other side, and the pi h squared, just divide it over to the other side. So, or multiply both sides of the fraction, or pardon me, multiply both sides of the equation by 4 over pi h squared. And what that'll give you is the following. You'll have dh dt is going to be equal to 4 over pi h squared times dv dt. That's what you get. That's what you'll get if you carefully solve for dh dt. So now we have everything we need, right? Because we know what h is at the moment in time that we care about. H is equal to 3, and we were given that the rate that the volume is changing is 2 meters cubed per minute. So dv dt is going to be equal to 2, and that's everything, right? The 4 and the pi, those are constants. So now we're ready to plug everything in. So we get 4 over pi times 3 squared multiplied by 2. Right? So what you're going to end up getting is 8 over 9 pi. And that is our dh dt at the particular moment in time that we care about, when the water level is, where the water is 3 meters deep. Because that's what we were looking for. That's what it specified at the end of the question. So now we're done. So let's just specify our answer. So I didn't leave myself very much room, but we can fit it in down here in the bottom corner. So the water level is rising. At 8 over 9 pi, what was it? Meters per minute, right? Because the water level, h, that was measured in meters, and our unit of time was minutes. And that was given to us at this stage. The time is measured in minutes, so we have meters per minute. And that is our answer.